everyone. It is my great pleasure to introduce today our neighbor and colleague from Florida International University in Miami, Professor Alex Krasnok. Alex has been working in several different interdisciplinary areas of nanoscience, nanotechnology, and photonics. And he has made significant contributions in areas of light scattering, different nanostructure designs, nanoantennas, metasurfaces, 2D materials, and quantum applications of various nanostructures. He's an expert and pioneer of several fields, including low-loss dielectric nanostructures. He has some awards and medals, including a Medal of Nobel Laureate, Alferov Foundation, Early Career Award in Nanophotonics. It's a great pleasure to have him here. He's also a founding director of Photonic Core Facility.
I was.
Are you? Oh, you are. Okay. Yeah. Okay, good. And so today he has an impressive publication list of a lot of papers and high impact factors. And I encourage everybody to check out his CV and to see some various areas of overlap. And today he will tell us a broad overview, I believe, of his work in photonics and quantum physics and some applications. And it's a great pleasure to have you. Please, the floor is yours.
Thank you, Dim, very much. And if you don't mind, I turn off my camera to make it the internet traffic better.
Okay,
so, yeah, thank you very much for coming. It's a great pleasure for me to give you this colloquium seminar. And as you can see, I slightly adjusted the title of my presentation to like a rather broad one: Photonics and Quantum Physics, Recent Breakthroughs and Applications. And yes, again, thank you very much, Dima, for hosting me. Like 2 weeks ago, I already visited USF and I was impressed by your facility and your university. And yeah, I really enjoyed that trip. And yes, at that time I gave an informal seminar about like more photonics oriented and our photonics research results in photonics, nanophotonics. And this time I decided to cover another research area more related to quantum. And so this website, this slide illustrates the first page from my website of our group for quantum technology and metamaterials research lab. I joined FIU, Florida International University, just 6 months ago. Before that, I used to work with City University of New York, Advanced Science Research Center in Manhattan, New York. And before that, I spent a couple of years with UT Austin in Texas, and yeah, and natively I'm from Russia. So as you can see, my lab is conducts research in quantum materials, functional meta devices, and quantum and optical sensors, and other research areas. And yeah, here the website you can find the contact information. So if you shall be interested, please contact me. Don't hesitate to contact me. So, and today I will talk about quantum and quantum computers without going too deep, like only basics and motivation why we need quantum computers. And at the end, I will also mention some of our photonics research and how photonics can help bring this quantum era sooner than later. So traditionally, we start with this first Moore's law, which says that the number of transistors on a chip doubles every roughly 2 years, and until the very beginning of this century, it was true. It was exponential growth with the slope of 2. But unfortunately, recently, like about 15 years ago or so, this trend started saturate. And even though the total number of transistors still grows exponentially, this exponential trend is due to the number of cores, the number of processors, rather than the number of transistors per core. And this is also the reason why the operation frequency gets saturated, and sequential processor performance, and so on. And yes, and this trend cannot go like very long. And also there is a second Moore's law, which says that actually the price, the cost you pay to put more and more transistors per crystal, per chip, is also grows exponentially. So we need a new type of computer. And here I put several numbers. And for example, this very popular Motorola processor, in the year I was born, 1987, the characteristic size of one transistor was 800 nanometers. And even at that time, the transistor, the crystal, looked like this. So if you look at the microscope at the transistor, you will see this extremely complicated CMOS fabricated chip with a lot of transistors over there. And even in the electronic microscope, you can see how complicated this structure is. Then when I enrolled to university, the characteristic size of the transistor was already like by 10 times smaller, just 90 nanometers. It was Pentium 4. Then in the year when I defended my PhD, the characteristic size was just 28 nanometers. The year when I moved to United States, it was Intel Core i7. The size was 16 nanometers. And then the year when I got my first faculty position, 2018, it was already 7 nanometers. And just recently, this processor, Apple M1, like they claim the size of 5 nanometers, and we expect that it can go down up to 2-3 nanometers. But this is the basically end, like fundamental end. Why? Because when you make these transistors smaller and smaller and pack them very tightly, because of the broad wavelengths of single electron in silicon, which is roughly about 5 nanometers, the electron start tunnel from one we cannot hear you. Oh, yeah, I don't know why. For some reason, my mic was of anyway. Yeah, so I said that because of this de Broglie wavelengths of 5 nanometer in silicon, if you pack more transistors to a chip, you get this tunneling from one transistor to another, and you cannot control this. And today people try to invent and develop new types of transistors using or exploring this quantum transport physics of quantum transport. But there are some transistors were invented, but unfortunately all these approaches are not well scalable, right? It's not difficult to invent a new transistor, but it's very difficult to make this new technology scalable. So, on top of this, and actually this is even more important reason for why quantum computer is that classical computers are they handle quite well this polynomial complexity class of problems, which complexity scales polynomially rather than exponentially with the scale of the problem. But unfortunately, this is just one of the one class of the problems, and there is a more general class of problems, which is called non-polynomial complexity class, which scales, for example, which scales exponentially with the number of constituting elements, etc. And this type of problems cannot be handled by classical electronic computers. And apparently the first person who noticed this was Richard Feynman, who said that why we using classical computers to solve quantum problems, like to model quantum systems like atoms, molecules, rather than inventing a new computer, quantum computer, which would explore quantum properties of matter to solve quantum problems. And if this quantum computer would be invented, it also would help us to solve other problems. For example, other non-polynomial problems, including factorization of large numbers and unstructured data search, and of course, first principle calculations in atomic physics and chemistry, like designing materials, first principle design of materials, etc., etc. So a lot of problems that are not solvable using classical computers can be solved using quantum computer. And so Richard Feynman suggested this idea in 1981, and pretty soon David Deutsch in just 4 years or 3 years proposed a theoretical idea of how this computer could work. And then later in 1984, Peter Shor suggested a first quantum algorithm that a potential quantum computer can solve. And this work initiated explosive development in this area. And in just 4 years, the first experimental demonstration of a quantum algorithm using just 2 qubits has been demonstrated, and in the next year, the group led by Nakamura and Tsai, they demonstrated that superconducting circuits can be used for developing quantum computers. And in fact, now the vast majority of quantum computers use this this approach of superconducting circuits. And yeah, in 2007, people invented and developed a first controlled 2-qubit system and realized this quantum entanglement on a chip. And as you probably are aware, in 2019, the group from Google, they claimed quantum supremacy of a quantum computer. In their system, it was just 53 qubits, like shown here, coupled to each other and controlled with microwave pulses. And they have shown that this quantum system can solve a non-polynomial problem faster than a classical computer would do. And in the same year, the group of IBM also reported their quantum computer. And the state of the art, I guess, in this technology now is recently reported quantum computer consisting of 66 qubits by a group from China. And so how this computer works, or like I mean, I'm not gonna go too deep to this area because it's very complicated. I just wanna give you some basics to grasp, which will help to grasp the idea of how this system works. So, first of all, one usually thinks that only a very small system like electron, photon, and others have quantum properties, quantum effects. Apparently, it is not, and even microscopic systems can have quantum properties, and it depends on how fast a particular system loses its so-called quantum coherence, quantum state. This quantum state is described by psi function, denoted by in Dirac notation, it denoted by like this. And let's consider a generalized quantum system like electron or photon, whatever. This quantum system can move along several trajectories, let's say like classical trajectories, 0, first, second, and so on, a group of trajectories. And this system is described by psi function, I just said. If this system is in the quantum state, it's described by psi function. And in the Hilbert space, which is formed by these basic vectors. Basic vectors here are potential trajectories or the evolution trajectories of the quantum systems. You can use these vectors to form this Hilbert space, and then you can use this Hilbert space to represent your general state of your system, this psi vector, psi state, using this Hilbert space, and you can make or calculate the inner product of or projection of this general psi state to each of these basic vectors, and you get these coefficients C0, C1, etc. And the rules of quantum physics dictates that you can represent this psi function as a sum of these basic vectors multiplied by these projection coefficients C0, C1, and so on. And since this Hilbert space is complex, these coefficients are also complex, and the imaginary part give rise to the phase that this particle, this quantum system, acquires as it goes along this path. And this representation here is very important because it says that according to quantum principles, you need to take into account all these trajectories simultaneously. So, like before you do measurement, before you find your particle in one of these particular trajections, you have to consider your particle, your quantum system, move along all these paths altogether. And as you do the measurement to your system, you can only find your quantum system in only one state. For example, I do my measurement and find my quantum system in this state n with some particular probability of Cn modulus square. For practical applications, of course, we need something that we can control, and the easiest quantum system which we still can control would be a system with only two basic states, or like paths, like here, like shown here. So, by the way, I forgot to mention that exactly at 4 p.m. I have to run to another meeting. So if you have any questions, don't hesitate to ask them during the talk, if it works. So we select a system with only two possibilities, only two states, 0 and 1, and we call this a qubit system. A system with only two states. For example, in very famous experiment with double slits, you can make a screen with only two slits. These slits select only two states, and then these two states can interfere at some screen behind, and this interference creates this interference pattern. And in experiment with many quantum systems, you indeed measure this interference pattern of probability. And surprisingly enough, for example, you find a lot of particles here where the vast majority of the classical particles would be shadowed, right? No particles here, classical particles, but quantum particles, they create interference maxima here, and you find a lot of particles there. And so two states, and you can represent this psi function using two states with only two coefficients C0 and C sub 1, and this Hilbert space becomes just two-dimensional, very simple. And yes, but of course, using this the double slit experiment is not feasible for applications, and for applications we choose other qubits. For example, it could be a state of a system with spin 1/2, like either spin up or spin down. It is like two states, like here, state 0, state 1, up, down. And before we measure this particle, we have to consider this particle to be in both possibilities simultaneously. Another system is a photon. Photon has it is a vectoral particle with polarization, either up or left, right, or up, down, and you can use this polarization to realize a quantum qubit. Another another system is a two-level system, like an atom with just two levels. You can use them to realize a qubit, and yeah, we can even create a so-called artificial atom, for example, at microwaves using this Josephson junction approach. When we, I will say a few words about this technology soon. But using just one qubit is not possible to realize quantum computing. It is useful for other applications like quantum communications, just one qubit. But for quantum computing, you need to make these qubits interacting. And how we describe this interaction? So let's consider a two qubit without interaction. The general psi function of this system is described by simple the product of two psi functions of the first and the second system, and this result is so-called separable. So you can separate this state into states of the particular qubits. But when you make these qubits interacting, this system becomes inseparable, meaning that, for example, these coefficients C0, 0, you cannot represent this anymore like a product of C sub 0 times C sub 0. This is a new coefficient join for both qubits, and that's why we use this tensor product of both systems, and we call this entanglement. And this entanglement means if we do something with one qubit, the second one immediately feels this action on the first one. And if I have, for example, 3 qubits, now instead of 4 coefficients, I have 8 coefficients. And one can see that this number of coefficients scales exponentially as a 2 to the power of n. So making like if your system has only 20 qubits, you already get this like a number about million, and current state-of-the-art quantum computers, they have like 50, 60 number of qubits, so you get a huge number, and this huge number actually is a number of like columns and rows in your matrices that you multiply, and you can try, but even using a supercomputer, you cannot like do these operations with these huge numbers already. So, but from fundamental point of view, this is just 50 qubits. These qubits can be atoms. 50 atoms is virtually nothing, it's just 50 atoms. But you can encode a lot of information into these 50 atoms. Unfortunately, it's not that easy, and I will give you some problems or discuss some problems that we have in this area. So typical traditional quantum computer, first of all, it differs to the fundamental Turing machine in a way that it doesn't contain any memory part. So because all these operations are done like simultaneously using all these quantum possibilities, all these quantum possibilities in your system. So you don't need a memory, any like quantum memory. Of course, there are some other quantum computers that use quantum memory, but here I'm presenting the most used one. So typically you have some number of input qubits, and then that you set using classical pulses, for example, microwave pulses. Then there is some quantum circuit that runs some quantum algorithm, for example, Zhores algorithm. And then this result goes to the output qubits, and you measure the states of these qubits, and this measurement gives you a result. So the key point is that all this is working based on interference. So all these quantum possibilities, quantum pathways interfere, and these interferences are managed by a quantum algorithm that you use. And fortunately, to realize a generic quantum computer, we need only 3 single qubit gates and only 1 2-qubit gate. And typically, these 3 single qubit gates are X gate, Z gate, and so-called Hadamard gate. I'm not gonna discuss how they work, just give you an idea. So typically, you have a 2-level system like atom, for example, or nonlinear resonator, and your system can be in either 0 state and the first state, or in the superposition of both with a certain phase. And if you excite this system, it oscillates between state 0 and 1, and we call this vacuum-Rabi oscillations. And the phase of these oscillations depends on the duration of the pulse you send to these 2-level systems. So you just vary this duration of the pulse to control the phase of your qubit. This is how it works. And the 2-qubit system is a system which consists of 2 qubits. They are coupled. And the most important one is this C node, which is called controlled node. And this C node gate, what it does, so the truth table is here. So it gets control qubit and target qubit. And if you set this control qubit to 0 state, it returns the target one to the same state without change. But if you set this control qubit to the state 1, it flips the target qubit. The key point here to understand is that we never have either 0 or 1. We have the superposition of both 0 and 1, and this gate does all these possible operations simultaneously. Yeah, and also without going to details, I only say that we simply have a system of two coupled qubits, and we control them using 2 pulses of different duration and slightly different frequency usually. So this is how it works. Not a rocket science, but at the same time, it's very difficult to set all these pulses and to make the system working. So a few words about quantum algorithms. There are some traditional quantum algorithms like Deutsch algorithm or Zhores algorithm, and we can program them using some of these quantum simulation software, including these QS simulators, Cirq, Qiskit, Forest, etc. And I personally particularly like this Qiskit software. It is the software by IBM. They use this Python, and they have very nice tutorial system. So if you are interested, I encourage you to go to their website. And what they also do, they actually very nicely provide access to their quantum computers, not the state of the art, but roughly 20 qubits. So you can program some quantum algorithm and send to their quantum computer and run your program there using a real quantum computer. This is possible and for free. So if you so far didn't get the idea how it works, I just wanna bring this, I guess, nice example of how, that illustrates or can give you a idea how it works. So suppose you have a complicated maze like shown here, and you have some input here and output, and you even don't know if there are some direct path from input to output. And this maze is very difficult. And if you ask your classical computer to solve this problem, your classical computer will go and try all these possible ways one by one. And if your maze is complicated enough, it will take forever for a classical computer. But you can say, or for example, if you find yourself in lost in a cave, like here, what you would do? You wouldn't run and try all these possible ways in the cave, right? What you would do? You would give a cry, right? What it means? You basically send an acoustical wave to all possible ways simultaneously. And if there are another person in the output, he or she will hear you out and will help you. And here I wanna show you the simulation, how it works for a quantum for a quantum system. So for example, I have some maze, and I just send a quantum wave into this maze and see what happens. So I see that my wave explores all possible ways from the input to the output, and it easily finds the way out. And the very important point here is this interference between different waves. So wavy properties of the waves, very important, but also this interference, destructive and constructive, of different waves in different paths. This is basically how, it illustrates how the quantum computer works. So here I put some numbers. These are state of the art in the area, and so the most powerful one, this quantum computer by IBM contains more than 100 qubits, and the vast majority of these quantum computers, they use this superconducting system, as you can see, with only two exceptions. One, Photonics, and this is very recently established research area, Photonics for quantum computing, and they have some advantages over superconducting. For example, they work at room temperature, but also some disadvantages as well. And another system using trapped ions also exist. And so, by the way, this number of qubits, actually, this is not a very reliable characteristic, because there are some quantum systems that already contain hundreds and even thousands qubits, but unfortunately, there are some more important characteristics there. For example, do all these qubits work together, or can you program this computer, and etc. So it's not enough just to fabricate 127 qubits. It's more important to make it like working in a way we want. So how we do this, or like how experimentalists do this? So first of all, what is quantum resonator? In fact, any resonator can be made quantum if you get rid of excitations. Like if we talk about microwave resonator, like shown here, if you remove all excitations, all noisy photons from this resonator, you know that at room temperature you always have some noise, and noise means a lot of photons with unpredictable phase, amplitude. If you get rid of them, you can make your resonator quantum. So to do so, we take our microwave resonator and cool it down first below the critical temperature to make it superconducting, to get rid of conducting loss, Joule loss, and typically it happens below 10 Kelvin. But unfortunately, it's not enough to cool it down to 10 Kelvin, because even at this temperature, you still have a lot of noisy photons at the frequency of interest. So that's why we need to cool it down even below 100 millikelvins, or even like up to 10 Kelvin, because at that temperature we get this regime when we have virtually zero photon in our cavity. And then we can put some photons and control the number of photons in our resonator like one by one. Unfortunately, it's not enough, because these spacings between different quantum states are equal, but we need to like select only two states, the ground state and the first state, to turn it into a qubit, like two-state system. That's why we need something like nonlinearity to put in the system. And in the superconducting area research, we use these Josephson junctions because they are lossless, virtually lossless, and at the same time provide a huge amount of nonlinearity, so you can select only two states in your system. And this is how it looks in electron microscope. This is just two metallic elements separated with very thin layer of dielectric. And then you can fabricate this system, this qubit, top of a chip. Then you can put some control elements there, nicely control the system, connect this one to another qubits, etc., etc. So speaking about challenges, so the first challenge is how to protect this really fragile quantum state, this psi function, from interaction with the environment. And we call this how does it, the quantum coherence time. And so this figure illustrates the progress in this area, and as you can see, the this quantum coherence time was growing rather exponentially. So one can also like think about another Moore's law for quantum computers, but unfortunately, this progress here with good qubits that preserve this quantum state for a long time, up to seconds, are based on putting these qubits into a three-dimensional resonators, and unfortunately, these systems make the quantum gates slow than like typical transmons, etc. So it's not a panacea, and researchers, a lot of groups are still working on how to make these qubits more reliable for quantum computers. More practical challenge, another one, is how to connect all these hundreds of qubits to a microwave facility. For example, this computer contains only, like, for example, 20 qubits, but even for this amount of qubits, you already get a bunch of these microwave cables and a lot of apparatus, facility connectors. So it's very difficult to handle or to control all these qubits using microwave systems, and a lot of groups working on how to make this this approach more feasible in that respect. Another challenge is associated with this channel. So so this is the scheme of the typical quantum computer. So we have this quantum chip over here, cooled down to 20 millikelvin, and you can control this chip using inputs and input coaxial cables. But you need to get some information out, of course, using this cable over here. But taking information out means that the transmission here must be very large. At the same time, according to the reciprocity principle, if your transmission is high in this direction, that means that transition in the opposite direction will be also large, meaning that the noise from the room temperature apparatus will go to your 20 millikelvin quantum processor, and this noise will destroy the system. So you need some isolators for your system, and typically we use these magnetic-based isolators and circulators shown here. But unfortunately, magnetic-based systems, they are lossy and contribute more noise. And also, magnetic field, in contrast to electric field, is very hard to screen because of no magnetic charges in nature, right? And magnetic field is harmful for the superconducting systems. That's why a lot of groups are working on more reliable systems, non-reciprocal systems for quantum computers. And yeah, this illustrates the idea of magnetic-based isolators. And in our group, we recently invented and developed the systems based on quantum nonlinearity. So what we do, we consider a waveguide with two coupled atoms or qubits, and quantum qubits, they are intrinsically nonlinear because of the saturation nonlinearity. If you put one photon into this two-level system, the system cannot absorb any more photons because it's saturated. So, and we can use this saturation to realize quantum isolator with this nonlinearity. And in our recent paper, I refer to Advanced Quantum Technologies journal. We published this story where we have demonstrated isolation up to 40 decibels with pretty high transmission in the forward direction. And one can think about using this system for quantum computers. And in fact, the very relevant approach has been recently demonstrated experimentally by our friend Professor Fedorov from Australia. And they demonstrated this nonlinearity in the realistic quantum system waveguide with 2 qubits. And yes, and we're still working in this area to make it working better. Another approach, of course, would be to use novel materials like topological materials, for example, Weyl semimetals. And this is our very recent work that has been submitted for publication very recently. Here we consider 2 Weyl semimetals to realize another type of non-magnetic isolator suitable for quantum computers. And so when we talk about computers, actually, typically we have in mind something like here on the right rather than the system on the left, right? So one can ask, can a quantum computer even potentially be personal? And of course, the answer is no. It's very specialized system. I have just 7 minutes left, so I'm gonna wrap up my part about photonics. I just want to say that, yeah, instead of quantum computers, we can consider so-called photonic computers, optical computers. And this brings us to point why photonics. So today, roughly 80% of information is carried by these optical fibers between database between different countries. But this technology has a very nasty bottleneck, because even though you use optics for communications, for example, right now I'm using internet, and my voice is converted from electronics on my side to optical pulses, and then these pulses go to your data centers, and these data centers then convert this information back to electronics, which is very nasty. And this conversion is very inefficient and consumes a lot of energy, according to US DOE recent report. And we think about processing optical information using all optical computer rather than electronic computer. But unfortunately, to do so, we at the state when we can realize optical computer, but it will be huge. Why? Because the size of the photon. So people think about photons as very small particles, but in fact, the typical size of a photon is roughly 500 nanometers, which is thousands times larger than the size of electron. Meaning that any optical transistor you realize will be 1,000 times larger than electronic transistors, and making the optical system very large. So we need to somehow squeeze down these photons to a nanometer scale. And to do so, we use this approach of nanoantenna. Nanoantenna is a resonance system that does exactly this. It localizes light into a very nanometer scaled areas on a chip. And like here, for example, these bow tie antennas shrinks down the photon to 1 nanometer sized area. And another reason why photonics is because very recently, we invented a lot of novel quantum materials, except for graphene, very famous one. Now we have two-dimensional transition metal dichalcogenide, and in group of in Dima's group, they work a lot on the two-dimensional transitional metal dichalcogenide for different purposes, and also we have quantum dots, perovskites, and V-centers, and so on. And in my group, we do investigate research in all these areas, and here are just some of our very recent results. Without going to details, because I have no time. Again, if you are interested, you can look through my website and contact me for any details afterwards. So, just to conclude this part, I show this slide with the state-of-the-art technology. It's so-called hybrid optoelectronic processor, where electronic part is boosted with optical components. This work is kind of outdated, published 7 years ago, and this is just to illustrate that we have some progress, nice progress, and most likely our future computers will be based on these optical components as well. Another technology that revolutionized our world right now, of course, this is artificial intelligence, and it turns out that photonics is very promising for artificial intelligence, because it allows us to realize artificial intelligence system using these optical components nicely on a cheap, very compact, and very scalable, which is very important. Another technology is lidars that allow our vehicles to communicate, for example, in the crowded cities, and quantum computers. Of course, this work has been published 2 years ago in Science, and this was the very first quantum computer. And why photonics? For example, as I mentioned, one of the most important quantum gates is this Hadamard gate, and in optics, this Hadamard gate is simply a beam splitter. So you put beam splitter, and it creates your Hadamard gate without any problems. There are some problems there how to create 2-qubit gates in optics, because photons don't interact without nonlinearity. So, and this is a huge problem, and this is actually the reason why this system is so large. So, some points to take home. Quantum computers are absolutely essential for tasks beyond the reach of classical electronic computers, and the current process in the field of quantum technologies, although outstanding, is the only beginning, and research in this area needs a new generation of quantum engineers. And here at FIU, I recently established a new course for quantum technologies and quantum materials, just to advertise my my teaching work here. Also, optical and hybrid computers will be the next generation of professional and personal computers, most likely. The peculiarities of photons make us explore new materials and their optical properties. And finally, optical technologies and their combination with quantum technologies open a number of important applications that are changing our world right now. So thank you for your attention. I just 1 minute behind the schedule, and unfortunately, I have to run to a very important kickoff meeting. So if you have maybe just 1 or 2 quick questions, I'm here and happy to answer them. Thank you for your attention.
Thank you, Alex. One or two questions, anybody?
Could I ask a question about the isolators?
Yes.
So you mentioned that kind of conventional microwave isolators pose a problem because of the magnetic field. And are you referring to, so a lot of microwave isolators have a permanent magnet in them to bias the material out of plane. Is the problem the stray field from the biasing magnet, or is it intrinsic to the materials that are used for the non-reciprocal transmission?
So for that purpose, of course, yes, we have these ferromagnetic materials, and you can.
So I guess my question would be: would that problem go away if you used materials that had intrinsic perpendicular anisotropy for the propagation of the microwaves?
No, no. So any kind of anisotropic materials are reciprocal. So there are only like maybe 2 or 3 approaches to achieve non-reciprocity. One, of course, is magnetic field. I mean, because you need to break time reverse and symmetry. Yep. So magnetic field is one approach and most like widespread. Another approach is nonlinearity, but there are some fundamental problems there. For example, it doesn't work well when you have 2 signals, like incoming and another one from another port, and that's a problem for this nonlinearity approach. And the third one is time modulation. When you modulate your system in time, like Floquet, it's called Floquet approach. Yeah, so only these 3 approaches, and of course combination of them. But anisotropy only is not sufficient for that, unfortunately.
Okay.
Yeah,
right.
Thank you for your question. Yeah.
Thank you. Any more questions? Anybody else? Last chance. Alex has to run.
Yes. So yeah, thank you very much for listening, and it was great pleasure for me. And if you are interested, reach out to me directly using my email. You can easily find it on the website. And again, thank you, Dima, for very nice and kind invitation for a previous seminar and for this Colloquium seminar. My great pleasure.
Thank you, Alex. Great talk. Nice to have you.
Yes. Have a nice day, guys, and thank you.
Thank you.
Thank you.
Thank you all.
Thank
Bye-bye.
you, everyone.
Bye-bye.
Bye.